With curves, we have a parameterization, vector value function of a single variable. And we'll assume that all these curves and surfaces are, even the curves are in 3D. But here we have two parameters, of course, for a surface. All right. Now, we have for curves, we have a tangent vector that we care about, and that's going to be r prime of t. Whereas with surfaces, we have a normal vector that we need to compute, do anything involving a surface. So we take partial derivatives with respect to u, partials with respect to v, and take a cross product, and that gives you a vector that is normal to the surface at any point. So we have here a curve and the tangent vector. Here we have a surface and the normal vector to the tangent plane. Okay. Now, curves, one problem with curves is computing the length, the arc length, and so you know how to do that, or you should. So integrating a function 1 over a curve ds, but the way that translates into parameters is the magnitude of your tangent vector, dt. Whereas with surfaces, this is what we covered last time, you compute the area. And that would be the double integral of your normal vector, ru cross rv, over the domain where your parameters lie. So here we have t going between a and b. Here we have u and v belonging to some domain d. It could be a rectangle, but it's some two-dimensional region. Okay, so this is how we compute the size of these objects. Now, we're at the point where we left off last time. How do we integrate functions over surfaces? Well, it's kind of like how we handle curves. So, to integrate a scalar valued function over a curve, this is what we've done this before, we get the integral of function f ds. And all you do is, whereas before we had 1 here, now we're going to fill in a function evaluated at your parameterization, x, y, and z of t. And then you still have this factor in here. So the line integral of a scalar valued function, it's just like computing the arc length, but whatever function you're integrating, you stick that in there. You evaluate it at your parameterization. Right. Now, that's old news. But we do the same thing if we want to integrate a function over a surface. So we have the integral over a surface. And what we do there is we put a function, evaluate the parameterization, r of u v, and then you put the magnitude of the normal vector, just like we did before, du dv. So computing an integral of a scalar function over a surface is just like computing the area, but you put your function in here, evaluate it at the parameterization. So that's what you plug in for x, y, and z. I notice that the filled-in upper half of the board is becoming more and more interesting. They're like wacko Christmas trees or something. Yeah, I was going to say, get a shot of that. All right. I don't know if it'll come out, but...
Kinda.
Yeah. Okay, so let's do an example integrating a scalar valued function over a surface, and then we'll take a look at vector fields. So, okay, so we have surface S with this parameterization. Cosine, u cosine v, u sine v, and v. Over here. All right. Now, the function we want to integrate really this should be a double integral since we're taking a two-dimensional object. All right. So the integral of a surface of this function, square root of 1 plus x squared plus y squared. Okay. So in order to compute this, which corresponds to this left integral down here, we need to fill in for x, y, we just have x and y, we don't have z. We need to fill in these functions. This is x, y, and z, functions of u and v. And then we have to compute from our parameterization of a surface this cross product and take its magnitude. Right. So we need the partial derivatives of our parameterization in respect to u. So that's cosine v, sine v in 1, and with respect to v, so we have minus u sine v, u cosine v, oh, that's 0, and then we have 1 over here. Okay. Then you need to cross product of these, ru cross rv, so we're going to have sine v times 1 minus 0 times this, so it's just sine v. Then we have 0 times this minus cosine v times 1, so minus cosine v. And then now, for the final component, we're going to have u cosine squared v minus the product of these two, which will give us plus u sine squared v. But that's just going to simplify to u. So we're going to have sine v minus cosine v and u. Okay, now we just need the magnitude of this. So that would be square root of sine squared v plus cosine squared v plus u squared. So we get 1 plus u squared. Wow, it worked out nicely. Okay. See, that's one of the things that the books don't tell you. That when you have an integral like this, it involves the magnitude of a vector, we're going to be taking the square root. It is really, really easy to come up with a problem that would be impossible to do. No, I'm not going to do that on the exam. I mean really impossible, not just long and tedious and evil.
So you're not going to do the long and tedious and evil one?
Not this time. There are other ways to challenge. Okay. So now we can write this whole integral in terms of u and v. Okay, I forgot to mention the bounds for u and v. U runs from 0 to 1, and v runs from 0 to pi. So now we're going to have the integral from 0 to 1 in u, 0 to pi in v. We'll fill in this function with v substituted for x and y. So we're going to have square root of 1 plus